Hello and welcome to this video. We are going to be learning how to derive the integral of sec x. So in other words, we want to prove that the integral of sec x is equal to natural logarithm of sec x plus tan x. So how do we go about that? Let's begin right away. The integral of sec x dx is still the same thing as the integral of the reciprocal of cos x dx. Now there is no direct way of integrating this particular function 1 over cos x unless we make some special assumptions. Okay, so let's begin by saying let a be cos x. Is that okay? Now if you make this assumption, it will also be wise if you can picture it using right angle triangles. So let's just get a right angle triangle to illustrate what we're trying to do. Now this is a right angle triangle and this angle is x. So since cos x is equal to a over 1, which is adjacent over hypotenuse, I can call the adjacent side a and the hypotenuse 1. Therefore, if we use Pythagoras theorem to simplify the opposite side, we'll get 1 minus a square. Now I'm going to use this as my reference right angle triangle to solve my problems. Now as you know, we called, let's go back to this point where we called a cos x. So if we differentiate both sides, the a should be minus sine x dx. In other words, the x should be equal to minus 1 over sine x dA. Okay, so what I'll now do is my integral of 1 over cos x dx is now equal to my integral of 1 over a dot, check this out, dx being 1 over minus 1 over sine x dA. Okay, so you now have your integral to be in this form, minus 1 over a, then 1 over sine x dA. Now from our reference right angle, we are going to evaluate sine x. Now if we evaluate sine x from our reference right angle, we'll get sine x is equal to root 1 minus a square over 1, which is root 1 minus a square. Is that okay? So sine x is root 1 minus a square. So the implication is that we have minus 1 over a, then you have 1 all over the square root of 1 minus a square dA. So this is where we are at right away. So let me just write it in this form. You have minus integral of 1 over a, then 1 over a root 1 minus a squared, then dA. So let's figure out how to integrate it from here. Now to integrate it from here, you have to make a substitution, and without beating around the bush too much, this is the substitution that you're going to make. So let p be the square root of 1 minus a squared. So we're going to integrate this by substitution, and we'll make p equal to the square root of 1 minus a squared. So what happens when we differentiate p? So this is still the same thing as 1 minus a squared, or raised to the power of 1 over 2. We then differentiate p with respect to a. So dp dA is equal to, first of all, you bring 1 over 2 down, then you're now going to differentiate what is in the bracket with respect to a. It will give me minus 2a. You rewrite the bracket and you now subtract 1 from the power. So this gives me minus a into 1 minus a square raised to the power of minus half. So another person can write it like this, minus a over the square root of 1 minus a squared. So let me assume you understand how we transitioned to this point. So in other words, dp is equal to minus a over root 1 minus a square dA. Okay, so the essence of introducing a new variable dp is to convert our integral into the p variable. So if we make dA the subject of the formula, what we are going to get is minus root 1 minus a squared over a dp, like this. So we're now going to do some substitutions into the integral. So please recall that p is equal to the square root of 1 minus a squared. So if p is equal to the square root of 1 minus a squared, p squared will be 1 minus a squared, and invariably our a squared can also be written as 1 minus p squared. So I'm just going to leave this one as a reference for later, or our a can be written as the square root of 1 minus p squared. Now let's go back to the main integral. So in the main integral we have minus 1 all over a, then we have 1 all over the square root of 1 minus a squared. Then instead of dA, I'm now going to replace it with what I have for dp, which is minus 1 minus a squared over a dp, like this. So what happens, we'll do some cancellation. This minus sign inside here is going to cancel out this one outside. The minus sign cancels out, so this cancels out this, so we are left with 1 over a squared dp. Alright, so this is integral of, so a squared, we've gotten an expression for a squared here, so it is 1 minus p squared dp, like this. And this is still the same thing as integral of 1 all over 1 minus p and 1 plus p dp. So at this point we can now use the method of what, partial fractions, to evaluate our integral. So consider 1 all over 1 minus p and 1 plus p. So it should be equal to a over 1 minus p and b over 1 plus p, like this. So we are going to use cover up method. A is the limiting value as p tends to what? Now in using cover up method, the linear factor under a is 1 minus p. So I want to look for what I'm going to substitute into this linear factor to make it 0. I can simply equate it by 0. So equating it to 0, I'll get p is equal to 1. So if you put p equal to 1, this particular linear factor will be 0. So our limit should have a value of p that will tend to a number such that when you place it into this linear factor, it will be 0. So in this case, the limiting value of p will tend to 1. Then you're now going to write the original fraction here, except that when you're writing the original fraction, you're now going to ignore the linear factor for that is under a. So it's going to be 1 all over 1 plus p, because we have covered up 1 minus p. Now if you evaluate this, you get 1 over 1 plus 1, which is equal to 1 over 2. So this is just a summary of cover up method. You can look up K. Stroud to learn more about the cover up method. Then b will be the same thing. You have limiting value. Of course, you agree with me this time around that to make this particular linear factor become 0, it have to be minus 1 that you substitute in for p. So when you write the original fraction, we are going to skip the linear factor under b and we'll be left with only this one, which is 1 over 1 minus p. So when we evaluate, we get 1 over 1 minus 1, which is still the same thing as 1 over 2. So both a and b are 1 over 2. So our integral, or our partial fraction, 1 over 1 minus p 1 plus p, is still the same thing as 1 over 2 into 1 minus p plus 1 over 2 into, okay, all over 1 plus p, and this is still the same thing as 1 over 2 into 1 over 1 minus p plus 1 over 1 plus p, like this. So our integral, which was formerly 1 over 1 minus p and 1 plus p dp, has now become 1 over 2 for short into 1 over 1 minus p plus 1 over 1 plus p dp, like this. So this is our integral. So continuing in this level, we now have 1 over 2 integral of 1 over 1 minus p, okay, or let me just rewrite it, plus 1 over 1 plus p dp. Now here's what is going to happen. We're going to distribute the integral like this. So 1 over 2 integral of okay, 1 minus p, sorry, dp, plus integral of 1 over 1 plus p dp. So we just distributed the integral, okay. So distribution of the integral sign, we're distributing it to each terms, okay, in the integrand. Now we want to evaluate this integral and this integral carefully. So to evaluate something like this, now the integral of 1 over 1 minus p, let me assume you already know the answer, but for the sake of those of us who might have forgotten how to evaluate something like this, it's pretty much easy. Assuming you were differentiating 1 minus p with respect to p, you're going to get minus 1. In other words, d of 1 minus p is equal to minus dp, or minus 1 dp. Is that okay? So in my integral, I have a 1 in the numerator position over here, okay. So is there something I can do to make it minus 1? Yes. So this is how I'll rewrite this integral. I'll write it like this, minus 1 all over 1 minus p dp. And I'll now put a minus 1 outside, okay, because there was no minus sign initially. So whatever I'm doing here, I have to create a countermeasure, okay, to cancel the effect of introducing this minus sign. So the reason why I had to introduce this minus sign inside here was to make the process of integration simpler, so that it becomes minus 1 integral of, so minus 1 dp now becomes d of 1 minus p, okay, and this is now in the form integral of 1 over something d something, 1 over something d something. When you integrate 1 over something d something, you're going to get ln of what? That thing. Is that okay? Plus our integration constant. So when you integrate 1 over something d something, you get ln of that thing something. So in other words, I just want to apply it here. I'm going to get 1 over 2, then the big bracket. So this one is minus ln 1 minus p, then plus, if I follow the same principle and integrate this particular one over here, I'm going to get a ln 1 plus p, okay. Then let's just say plus constant of integration. Now if you rearrange this, you'll be getting 1 over 2 ln 1 plus p, then minus ln 1 minus p. Is that okay? Plus c. So where are we going with all of this? Let's keep moving. So we have 1 over 2. Applying the law of logarithms, you have ln 1 plus p over 1 minus p, then plus c. Now this becomes ln square root of 1 plus p over 1 minus p plus c. Of course, you know that ln half ln a is still equivalent to the square root of a. So that was the principle I used in coming to this particular direction over here. So now what do we do? Now just recall that a Okay, recall that P was given 1 minus a squared. So since P was made 1 minus a squared, invariably, if you go back to our triangle, our reference right angle triangle, sorry, you discover that here was a and here was x, here was 1, and this place is 1 minus a squared. Now if you take sine x, you're going to get 1 minus a squared over 1. So invariably sine x is actually the square root of 1 minus a squared, and this is equal to what we have as p from all our substitutions. So this thing is still the same thing as this is the integral of sec x dx. It's still the same thing as ln square root of 1 plus, anywhere I see p, I'll replace it with sine x over 1 minus sine x plus c. Okay, so how do we proceed from this point? Now we are now going to rationalize the denominator in this case on the right hand side. This is how I'm going to do it. Ln square root of, so I have 1 plus sine x, rationalizing I have 1 plus sine x over 1 minus sine x, then 1 plus sine x, okay, and plus c. So this gives me ln square root of 1 plus sine x all squared over, when you apply difference of two squares to the denominator, you get 1 minus sine squared x, like this, and this gives me, okay, don't forget your integration constant. Okay, so having done this, I want us to recall a very important identity, that cos square x plus sine square x is equal to 1. So anywhere we see cos square x, we can still call it 1 minus sine square x, and anywhere we see 1 minus sine square x, we can call it cos square x. So our integral of sec x dx is equal to ln square root of 1 plus sine x all squared divided by, this is cos square x and plus constant of integration. So you have ln, I'm gonna distribute the square root symbol to the numerator and the denominator like this, over square root of cos square x plus c. So if you do it like that, you're going to get ln of 1 plus sine x over cos x plus constant of integration. Now after doing it like this, you can now distribute the denominator to each terms in the numerator like this, plus sine x over cos x plus c. And finally the integral of sec x dx becomes ln 1 over cos x is sec x, and sin x over cos x is tan x, plus constant of integration. So this is the proof that the integral of sec x is natural logarithm of sec x plus tan x plus c. Okay, I hope you enjoyed the video. Don't forget to like, subscribe, share, and next time we're going to see the integral of cosec x dx. Okay, so you can actually try it by yourself, but we're going to try to prove that the integral of cosec x is actually going to be minus ln cosec x plus cot x plus constant of integration. So it's just following the same principles. You have to make the assumptions, and you have to picture an imaginary right angle triangle that are having sides that are proportionate with the assumptions that you made. Previously we obtained that the integral of sec x with respect to x is natural logarithm of sec x plus tan x plus c, but I'm not actually writing it in the exact form it's supposed to be, and that is what I want to do now. The exact way of writing this particular integral is this. Integral of sec x plus dx is ln absolute value of sec x plus tan x plus c. So this is just perhaps this first one is just the informal way of writing it, but this one is more formal, and the reason can be explained if we trace our steps back to this point. We're going to trace our steps back to this point over here. So I'm just going to recopy what is here and we'll examine it like this now. So we have ln square root of 1 plus we have sine square x over sine x all squared, ln square root of 1 plus sine x all squared over square root of cos square x. So let's explain why it's like that. So having seen that, we can now see that the reason why I want to express my integral of sec x with the absolute value symbol is because when we got to this point, we had a ln square root of 1 plus sine x all squared over square root of cos square x plus c. Now if you agree with me now, the square root of a, literally if a is a variable, you can take the square root of a as plus or minus a. Is that okay? So what we are supposed to be having is equal to ln plus or minus, in the first case we'll get 1 plus sine x, then in the denominator we'll have plus or minus cos x, like that, plus c. Now there is a problem with expressing it like this, and the problem is going back to this logarithmic function. So ln x, so this function has a domain that is like this. We have it takes numbers from 0 to infinity. Okay, so there's no, it takes input, that's input values of x between 0 and infinity, and we don't actually include 0. So any other number that is greater than 0 upwards, the ln function can work with those numbers. But guess what? The ln function cannot work with negative numbers. So since the ln function cannot work with negative numbers, for our real domain, if you find ln of minus x, it's actually undefined. Okay, ln of a negative value of something does not actually work in the real domain. But later on in a video, I'll explain the ln of negative numbers, or the logarithm of negative numbers. Logarithm of negative numbers does not exist completely on the real number system. We'll have to cut across to complex number system, and trust me, that one is going to be a video for another day. So just try to understand what I'm saying, that by virtue of the fact that we're still in the real domain and we don't want to include a case where we'll be dealing with the logarithm of negative numbers, for this particular expression we'll have to maintain our stance in the real number system. That is why at this point I'll have to introduce an absolute value symbol, 1 plus sine x, okay, all over the absolute value of cos x, like this. So I'll have to introduce it this way, okay. So the reason of introducing the absolute value symbol is to maintain us in the real number system. So what we're simply doing is we're going to take the positive values of the square roots, okay, the positive value of the square root, and we're not going to consider the negative values of the square root. So the integral of our sec x dx is going to be ln, okay, and we have 1 over cos x plus sine x over cos x, all in the absolute value symbol, plus constant of integration, which gives me ln absolute value of sec x plus tan x plus c. So we have integral of sec x dx to give us this value that you're seeing here, and the absolute value symbol is because the logarithm function does not accept negative numbers, which would have been the case when we allow the literal meaning of taking square root. When you take the square root of something, you should have a plus or minus of that particular thing, but this time around we want to consider just the absolute values of whatever this ratio gives us, okay, whatever this ratio gives us, okay, ignoring the fact that there is actually a square root symbol. So this is a more formal way of expressing it. So anything that is evaluated here in this bracket must be greater than 0, okay. So that's the meaning of this absolute value symbol that you're here, and the reason why it should be greater than 0 is so that the ln function will still remain in it, will still be able to evaluate values or evaluate inputs that are in a valid domain, okay, that are in a valid domain. So you can check up, or you can, I believe you've done domain and range before, so you should try to check up the meaning of domain and range, so that you can learn the domain of various functions. Learning the domain of various functions will help you understand more, while we had to express this formally in this particular form, okay. I hope this video has helped you again. So this is it about the proof of integral of sec x with respect to x. So thanks for watching the video once again. See you next time.